question is it safe to adjust osteoporotic patients with an activator adjusting instrument? And that was what our whole goal was. Now, all of this safety and efficacy started way back in 1985 with an NIH grant. I got the first small business innovative research grant for $50,000. We thought we had died and gone to heaven till we found out at the end that it actually cost us $100,000 to do the project. So, but it got us started, and we were so excited about being NIH grantees. This is what we looked at, and the project title was Safety and Efficacy Instrument for Spinal Adjusting. The very first time that we tried it, we used ultrasound. And everybody was all excited because we saw an atlas actually move. The only problem was we couldn't measure it. So we then had to find a different way to do the measuring that we could actually be able to calibrate it. So we went to Logan University and to the lab instructor there, and he had a 40-pound lab animal, and we put a pin into the spinous process and a transducer next to it and made a thrust, and we found out that on a 40-pound lab animal that the bone moved 1.3 millimeters a few milliseconds after the stylus displacement peaked. We were on our way. Now, we wanted to look at rotation also, so we went to St. Louis University Medical School. Now, remember back, this is almost 30 years ago, and it was a major coup to get into a university medical school to do this kind of a project for a chiropractic profession. And in the lab there, the NIH required us to have two different measuring types. We had to have the piezoelectric transducers that you see up by my hands, then also these optical electric cameras that you see, the blue cameras down here. And so that's what we did, and we were able to then measure not only the translation, but also the rotation. And we thought we were really moving along, and actually we were. We wanted to do this in a human, but in the United States, the institutional review boards wouldn't allow us to do it, the ethical boards, so we had to go to Sweden. Sweden didn't care. And so that was a graduate student that donated her body to science. We put Steinman pins in L4 and L5, and we started adjusting them up by T11, working all the way down to where the Steinman pins were put into the L4 and the L5. Here's what we found out. Up by T11, it moved 0.3 millimeters, and we'd expect that because we weren't close to where the pins were. Then down where L5 and L4 were, it moved 1.6 millimeters. Now, we didn't think that was a lot, but I want you to remember 1.6 millimeters. I have a reason for that. Then also we did a mathematical model, and I want you to see this. Even when you're adjusting with an activator, 4 more bones on each side, or 2 on each side, so 5 bones are actually moving at one time. So the people that think they're doing a specific bone are just wrong, that they're all hooked together. And so just think, even with as specific as an instrument is, we're moving about 5 bones. Then we said, well, if we're only moving a bone 1.6 millimeters, what about the people that turn people on their side and they use 540 newtons of force? Remember, we use 140. How far will that move? So the lumbar thrust was given, and it moved the bone 1.1 millimeter. It wasn't until many years later that Greg Kramer from National College explained to me why, because when you turn somebody on their side, the facets lock it, and actually it's a safety factor for the patient so they can't get hurt. But remember, with the correct line of drive, we were moving it more than you were with the lumbar roll. Now, how can activator move a bone with so much less force? Well, we start looking at it, the speed, and high speed was one of the factors. And we found out that we moved the bone, or we had a speed that was up to 200 times faster than a manual adjustment. But the real thing was the ideal waveform. It was the natural frequency of the human body. And we started to see if we could set an instrument up to be in the natural frequency of the human body. It's called a half sine wave. And so an ideal waveform is fast enough to stimulate mechanoreceptors, propagates more easily through biological tissue, and it enhances the frequency spectrum of activator device toward an ideal waveform that allows us to create more bone movement with less force. Now, here's an ideal waveform. There's a ideal waveform, and the activator 1 was about 35% of it. It wasn't too good. So we started then working. We put a 44-gram weight on the end of an activator 2, and we got up to 48%, making some progress. It wasn't until we got up to the Activator 4 and we put a preload on it so it had the same thrust each time that we could get up to 74% of the ideal waveform. So Activator 4, the most popular instrument that we use today because it's sturdy and it does the job. But the Activator is 4, but we thought, how can we even make it better? Because we wanted to get that perfect half sine wave. How do we make it easier to use, more comfortable, capture the even more ideal waveform? That's really what we were looking for. So we went to Baylor College of Medicine, and Professor Michael Liebschner was there, and he was an expert in biomechanics, and so he started helping us. We developed a test setup that eliminates user variability, mimics the compliance of biological human tissue, directly measures the load induced into the tissue, and we set a whole type of testing procedure up in a testing platform, and you'll notice that the actual body, what is rigid like the body is a test material, and behind that we put a resting load cell. Now, I have something to tell you here. We made a mistake. The engineers wanted to measure everything very precisely, so they fired the Activator into a steel beam. That got you what? Reproducibility. Except when Dr. Liebschner looked at this, he said, look, the body is not a steel beam, Marlon. The body is flexible. So he built two polymer blocks, and that's what you saw in the testing procedure there. And so there was a flexible one on the left and a rigid one on the right. There's a flexible. That's what happens in a baby's spine. And by the way, we now know how much force to use on 0 to 90-day-old babies. And then the more rigid spine. This is in the geriatric patient. So the Activator 5 produces a more transmissible force than all the other predicate or competitive devices. Get this word in your vocabulary called transmissibility. That is what force is transmitted into the body. Think of the body as that black line, and then the force starts over here on the left, and it gets into the body. It goes through that black line. That's called transmissibility. The ideal waveform, well, let's take a look now. Remember, the Activator 2 was 48%. The Activator 4 was 74%. But now with a autoprocessor where we can dial it up and dial it down and get it to the perfect waveform, we're up to 94% of the ideal waveform. That's plus or minus, and we're almost at a perfect waveform. That's why the Activator 5 to date is the best instrument we've produced. And there's a reason for using one. Not only that you can control it better, but also we found now in clinical practice that things like osteoporosis, things like muscular dystrophy, multiple sclerosis, Parkinson's, those are neurological diseases. The patients don't get a reaction, and the reason is because it goes in that perfect half sine waves and it doesn't irritate the nervous system. Now, the question always has been, how many thrusts per contact point should you use? Well, Richard Roy did his PhD on the effects of a manually assisted mechanical force on cutaneous temperature. And I want you to take a quick look at this because this is a thrust into the body. The first 0 here shows the first thrust. It goes from a warming to a cooling effect. But 4 minutes later over here, without touching the patient, it goes into another warming, cooling effect, then back to normal. And that's something the body does all by itself. So the answer is, how many thrusts should you use? 1. Let the body do the work. Now, Calcified Tissue International just published this paper in July of 2013, and it was out of the University of Madrid. And we started this whole project. We wanted to know the impact of chiropractic manipulation on bone and skeletal muscles of ovarian rectumized rats. And osteoporosis is defined as a metabolic bone disease characterized by a decrease in bone mass and bone mechanical strength causing susceptibility to fractures. And many times when people fell, they thought the fall broke the bone, but now they're finding out it was the osteoporosis that actually caused them to fall. Now, pay attention to this slide because recent studies demonstrate that proteins and growth factors called in general myokines and produced a skeletal muscle in response to contraction may affect bone mass. between these myokines, that's mechanical growth factors, is overexpressed with skeletal muscle stretching. But now current data have shown that the mechanical growth factor expression increased under mechanical stimulation on an osteoblast introduces proliferation. Thus, the mechanical growth factor is considered to be an important factor related to the beneficial effects of exercise in bone. And so this is what we did at the University of Madrid. And here you can see them using an Activator 5 on a lab animal. And I don't know if you know this, but osteoporotic rats are only grown in one place in the world, and that's Los Angeles, California. So we ended up buying 10 rats from Los Angeles and shipping them to Madrid to prove that we could safely adjust a lab animal with osteoporosis. Well, here's what we found out. We actually, not only was it safe to use, but you can see as you look over on the different slides here, this is control. You can see all the trabeculum in here. And here's the one that's actually got the osteoporosis in it. Take a look at it up here, and then go over here and take a look. This is after they were adjusted, and you can see it especially here. You can see this was all gone. It's now coming back. So the more they got adjusted, the more bone that grow. And so now the next step is to take this to humans, and when we go to humans now, we'll find out, does it work in humans? And we think it will. The Activator method is the only instrument that has 25 clinical trials to support its efficacy. And as you can see, it costs a lot of money to ship rats to Madrid to be able to do this particular type of a program. That's why we're #1 in the world in instrument adjusting. Which brings us to the end of this, and I just want to tell you a story that happened. We were at our 50th anniversary, and the researcher, Arantia Ortega from Madrid, gave this presentation in its entirety. And one of my clinicians who I've known for 30 years was sitting next to me, and he says, Arlen, he said, this is why, he said, people come in with walkers, and he said 6 months later they're walking without the walker. They're growing bone. And I said, well, that's a nice projection, and I hope that's true. But I said, at least you can be careful and be safe adjusting the patients to keep the pain down with them as they're having their problem. So look at the excitement we have here, and we just wanted to present this to you.